Good, so welcome back everyone. Sorry this is a little shorter break today, but I have a lot of content left, so we have to make sure that we get through with it. Yeah, so like I said, if you look at the formula, it should be clear that we cannot do translation with matrix multiplication in a regular way, but we are very interested, of course, in doing it with matrix multiplication, which is why we have this enhanced concept of matrices, which is then leads to the affine transformation. And the idea of it is actually something that we already saw today with the shearing. If you remember what I said at shearing, I kind of informally explained that by saying we're pushing things sideways at a certain level. And of course the coordinates change in that level, but everything that is at that level stays the same. So for example, for the shearing in the x direction in 2D, we had that the values that were sheared at this particular x value stayed at the same x value and got just shifted to the side. So they got moved to the side, they got translated. So we see here, and by choosing the factor s that we use for the multiplication appropriately, we can shift it, this part here that is on the line or on this level, to any position on the line. So we can do a translation here on the line. We can do a translation in a one-dimensional space, a subspace of our 2D space, which is then this line. So the 2D space is the plane, the line is the 1D subspace, and we can do a translation there by matrix multiplication in 2D. And the same goes for 3D. We haven't covered 3D yet. 3D transformations we will discuss at the end, but you can already imagine it, how shearing in 3D could look like. If you have a rectangle and you shear it with respect to the z-axis, then of course you can shear it in the x direction in this way. You could also shear it in the y direction or in both directions in the x and y direction, but you will always stay at the same level here, which is the same set value, the same set level, which in 2D means then you will always stay on the plane at this particular set level, the plane that is parallel to the xy plane. So what you do here is basically you do a translation of a 2D object in a 2D space by applying a 3D matrix multiplication. And that is the basic idea of these so-called homogeneous coordinates, which is an extension of the matrix concept, which then leads to these affine transformations. So the idea, just illustrated very simple with an example case, is we want to translate an object in 2D. So, but we know we cannot do this with matrix multiplication. But we know we can translate a 2D object in 3D with matrix multiplication. So what we do is we just introduce a third coordinate and then move to a 3D space. And that of course is done by just adding a 0 as a third coordinate. And then we are still within that 2D subspace that was our original 2D space. Now what we're doing is we're placing a copy of the original image that we have, or the original object that we have, at a certain level L. And then we have, again, a 2D image of that, but at a different level now, not in the xy plane, but in a 3D space. And if we apply the shearing to it now, we can shift that, we can translate it within that level. So we have translated this 2D object in the 2D subspace by a matrix multiplication in 3D. And then we do an orthographic projection, which basically means we just take the third value coordinate and set it to 0. And then we're back in our original 2D space. And we see now what happened is we took that object, which was just a copy here, translated it, and have it here. So we just did a translation in 2D with this object by going this detour over the 3D case by shifting that level, because then we could apply matrix multiplication. So we see here the basic idea should be clear. We are applying a matrix to a vector where we just have a third dimension at a certain level, and then we can achieve something like that, which is exactly or almost exactly what we want, which is adding factors to these coordinates. Now, the question is, of course, how does this matrix look like, and how do we make it the matrix in a way that we really add constant values here and not variables like we did before when we do a linear transformation? And of course, how are we going to deal with this third coordinate here? What's the deal with that one? So if we look at, let's first look at shearing in 3D. In 3D, of course, there are different ways to do the shearing, because you cannot only shear in X and in Y direction, because you can also use shear in Z direction, or in a combination of the two directions, you can shear in X and Y direction. And one of the ways to do that is with this matrix here. So you remember the 2D case, we just had 1, 1, 0, S, and then we're just shearing, of course, in X direction. Here we're shearing in X and Y direction, so we have two factors here. And if we multiply them with the vector, we get almost what we want, plus these factors here, but we still have this third coordinate here. But if you think about the basic idea that we said we're just copying in a certain level. I called it level because I think then the shifting is kind of more intuitive. Of course, it's not a technical term, it's more an informal description of it. But this level or this plane or this set value, we didn't specify anything about it. And if you look at the basic idea, there is also no reason why we should say if we shift it in a level up or lower, it doesn't really matter. So if we set this level to 1, if we shift everything at the plane set equals 1, then so we could apply this basic idea also to each level, including the level 1. But if we apply it to the level 1, then of course we have the situation that here we always have multiplication with 1, which basically means we just have these constant factors here, which is exactly what we want. So if we use a transformation matrix like this, where we add another column here that has the constant factors and another row that has zeros, because they don't change then, the result, and 1 here, then we get as a result exactly what we want, with the only exception we have this 1 here, which we then ignore or which we then remove by doing this orthographic projection, which basically means replacing it with a 0 and then throwing the third coordinate away. Good, so we see that this is a way to do translation with matrix multiplication in 2D by moving to this third dimension. And these additional coefficients that we introduce for that are then called the homogeneous coordinates. Now there is one problem with this. If we do this to a point, then of course we can translate it. But as I said at the beginning, if we're talking about vectors, of course if we use a vector to represent a point, then it's not a problem. But if we talk about a vector as an abstract concept, then of course a translation doesn't make any sense, because you remember a vector was defined by the length and direction, so there is no position. So if we translate a vector, it doesn't change the vector. But if we translate a point or a vector representing a point, of course it changes the point, because then and that way then also the vector representing it, because it represents a location that we can translate. So to deal with that, if we also want to manipulate vectors with affine transformations, we just have to represent them in a different way, and we do this just by having a 0 here. And then you see, of course, because then we have here plus 0, so that will mean we will always end up with a vector that we can apply the linear transformation to it, but not the translation, which doesn't make sense for vectors. So maybe a way to illustrate it or to understand the conceptual idea behind it. Think about, you have like a game where you have a character and you want to transform that character. So for example, you say it's a fantasy game, he drinks some fluids and then he grows in size by 2. So you want to apply a scaling matrix to it, and you also want to move the character to a different location. So you apply one matrix to it that moves and scales it at the same time. And now think about, you have this model and you want to put that model, give it to a friend so he can use it in his game. But before you give it to him, you don't want to give him this original model, but you want to have it scaled by the size of 2. And you already have this transformation matrix that scales and translates it. But since it's a vector, translation doesn't make sense. It would change the model also. So you just apply, you have to create a new matrix, which for scaling is not really that difficult. But if you have a more complex one, it's a lot of work. Or you could apply just the matrix from the affine transformation by representing the vectors with these zeros here. So it's always important to think about, does the vector represent the location? Then, of course, we have to have this 1 here, because then we also want to be able to translate it. If we have a vector that represents really a vector and not a location, but an abstract representation of a direction and a length, then we have to put a 0 here, because that way we can guarantee that it is not translated, but all the other linear transformations are applied to it. Good. Yeah, like I said, these additional dimension that we introduced is then called the homogeneous coordinates, and these homogeneous coordinates allow us then to do this affine transformations, which are linear transformations plus the translations. And we can combine them, of course, into one matrix. So we've seen, for example, if we look into an example where we scale and move, like I just said, we have a translation matrix and we have a scaling matrix. Oh no, be careful with the order. We have a vector, we want to scale it, and then we want to move it. So we can apply these two matrices, or we can combine them into one, and then you see it will exactly happen as we expect. We scale the original vector. So you see here this multiplication by adding this homogeneous coordinates to the scaling matrix doesn't change with the result of the scaling. And then we do the translation, and you also see that the translation doesn't change the result of the scaling. It just shifts the vectors by adding these constant factors here. So you see these two concepts, the linear transformations and the translation, fit very well nicely into each other, so they integrate seamlessly into these affine transformations that we can do now. And of course we see if we apply the same matrix to a vector, then of course we only do the scaling, but there are no values added here, which is of course important because we do not want to translate a vector. So even if we use a matrix that includes translation, we get only the operations that are reasonable for vectors, which are only the linear transformations and not the translations that are depending on a certain location, because a vector doesn't have a location. Good. And with that now we can do more complex operations like we had in the example before. Actually, I don't have the example here. I will leave that for an exercise. But I have another example where reflection on a line, which is again the same idea. Instead of doing a reflection on this line, we say, well, reflection on a line through the origin is very easy. So why don't we just shift everything to the origin, including these objects here, this original object here, and then we do the reflection at the line that goes through the origin, and then we shift everything back. That should be very easy transformations, especially now that we know how we do the translation. So let's look at the reflection at the origin first, if that is really easy, and it is of course easy. If you remember, we had a reflection at the line y equals x, and then we said we just swap the x and the y coordinates. If you think about what happens when you have a line y equals minus x, then you will see that it does not just swap the x and y values, but it also reverses the sign. So instead of 0, 1, 1, 0, we have 0, minus 1, minus 1, 0 here. So that is our reflection matrix. So all we have to do now is we have to make sure that everything here is around the origin, or that the line here that use for reflection goes through the origin. And we can do that by just taking everything and subtracting 0, 5 from it. For every point here, that will of course shift everything to that. We have a complete copy of our original scene just centered around the origin, so the reflection line goes through the origin. And we can do that with matrix multiplication. If we look at what we have to do here, of course the x value here stays the same, so that should be 0, and the y value is a -5, so that should be -5, and that is our translation matrix. Now the other thing is that we need, then the final thing is, of course, when we do the reflection, we want to shift everything back. And we can do that, if that is our matrix T, then we can just calculate the inverse of it. Or we could also look at the image, and then we also, of course, see that the inverse operation to that would just be adding 0, 5. So this is then, I wrote it here, the matrix we have for xt, we have again 0, and for yt we have 5. And the original one was 0, -5. And this one here, the translation matrix, the reflection matrix, was in 2D. But since we're combining it now with translation, we have to add these homogeneous coordinates. But if you do the multiplication here, if you multiply these first two matrices with each other, the translation and the reflection matrix, you will see that it doesn't change here this part. It only changes the translation part here. So you see here, these coordinates do not influence the linear transformation. They only influence the translation, which, if we combine it here, leads to 0, -1, -1, 0. So again, we still have the linear transformation here, 0, 0, 1. And here we have 5 and 5. And then we can represent the whole transformation here with one single matrix, which is the product of these three matrices applied in the correct order. So that is our final transformation matrix. Good. Now we set one way to come up with, now this, you see again, we have different ways to come up with transformation matrices, and that was decomposing it into single smaller steps that are easier to handle. But we also said we can use it by just looking at it and looking at the images of the base vector. We can come up with a solution for linear transformations, and that is the same still here. These are still the images of the base vector under the linear transformation, which is the one that we do around the origin. And of course that makes sense, because once we shift it to the origin and then we do the linear transformation, we're only looking at the base vectors of the image of the base vectors at this position, which are then of course these two base vectors where we basically shift everything to. Now for the translation, of course, that doesn't make sense, because for the translation we need to look into what is the we need to consider the whole affine transformation. And if you look at it, you will see that these here are exactly the image of the origin under the affine transformation. It's badly drawn here, but that should be the same value here, 5, 5. I almost hit it here. And it also kind of makes sense if you think about it. If you think about what would happen if you take the original origin and put it and apply the affine transformation to it, of course you end up at this point here, which means that this 2 points here must be the image of the origin. So that gives us another easy way to find the matrices. Instead of composing, we can also just look at the image of the base vectors under the linear transformation for this part, look at the image of the origin for the affine transformation for this part, and then add a final line, which are then the homogeneous coordinates to it. Good, and like I said, this is then something you can do as an exercise. Because, of course, we also want to address today the transformation in 3D. So the 2D case, we started with that, of course, because it's easier and also easier to draw, and easier to draw also means for you easier to look at and to understand. But the 3D case is actually not that much more difficult if you understand the 2D case, because in a lot of situations it's just a simple generalization of the 2D case. And in fact, we've already seen an example, which is the shearing in X and Y direction. But because we wanted to end up or use the shearing in a very specific way, namely to simulate these translations, I only introduced a very specific case of shearing where we only had the X and the Y values in the final column set to values unequal to 0. But of course, if we are not interested in the translation, but we want to do a general shearing, there is no reason why we shouldn't set these values also unequal to 0. And then of course we get a more general form of shifting shearing in X and Y direction. But you see here, because we have chosen set 0, 0, 1, the set value will always stay the same. So we are shearing in a different way than here, but we are still shearing only in X and Y direction, always in that plane that is at the same level as this particular set value, because the set value doesn't change. And that is why this is a general case for shearing in X and Y direction. And you see here also, this is an example for the generalization of 3D that we have. In 2D we can only shear in X and Y direction. In 3D we can shear in X, Y, and Z direction, but we can also shear in a combination of two of those. We can shear in X and Y, or Y and Z, or Z and X. And this is, for example, the shearing, and we already had the combination X and Y because we needed that for translation. But if we just want to shear, for example, in the X direction, which is actually what I did in this image here, because I didn't show the Y direction here, only shifted in X direction, then actually such a matrix would be sufficient. Good. All right, and in the same way, of course, as the transformation matrix, the linear transformation matrix is generalized to 3D, also the homogeneous coordinates generalized to 3D. But of course, now we have to shift to a fourth dimension. I already had the one image illustrating the 3D shearing, but I didn't have an image for the homogeneous coordinates because, of course, we have to draw that in 4D, which is something we cannot do, which is again the reason why I started with the 2D case and now are using just the generalization of it to explain the 3D case. And of course, with these homogeneous coordinates, we can easily do translation by having these values in the fourth column now, in 4D now. And then, of course, you see this is again a simple translation. And of course, we can also extend our other simple case that we had, scaling. We can scale with respect to 3 coefficients. We can also do reflection and rotation. Now, the difference between from reflection and rotation to 3D is that we have like a little more options here in the same way as for the shearing. We can shear in different directions. For rotation and reflection, we can reflect not necessarily on lines, but in 3D, for example, we also want to do, or more often want to do, a reflection with respect to a plane. And a rotation, in 2D we rotate usually with respect to a point. In 3D we often rotate with respect to a line, or like I wrote it here, a directed line. So let's look at an example for rotation first. Let's look at a simple case, which is, for example, a rotation around the z-axis. So if this is our coordinate system, and this is the z-axis, and these are x and y, then we want to rotate around the z-axis. Now, if you look at rotation in 2D, so forget about this here, just assume you have x and y, then we know the rotation for the x and y values can be calculated by this transformation matrix. We learned today why. Now, if you look at what happens to the x, y, and z coordinate in a 3D case, for the 3D case, the x and the y coordinate, they actually stay within that xy plane and are rotated in the same way as they are rotated in a 2D case. So for the x and y, we get exactly the same values here, which means we need to use the same coefficients that we have in the rotation matrix for the 2D case, for the x and y values. But what happens for the set value? Well, the set value, like I said, they stay in this plane. That means the set value stays the same. If we have a point here, it's rotated in that plane here, but it stays at the same level, at the same set value. So the set value doesn't change. So we need a transformation matrix that has the same for the x and y as in a 2D case, because they are rotated in the very same way. And it does not change the set value. So x, y, set, and the set value doesn't change. And that we can achieve, of course, by setting the x and the y to 0, and the set part of the sum to 1, the factor of the set part of the sum to 1. So we will then have 0 plus 1 times set, which is, of course, the set value. And I was already trying to draw it with a square to illustrate it, and then I stopped because I realized that might confuse you, because I used this notation here, somewhere here. And be careful, of course, that looks very much the same, but this is different. Here, these are not the homogeneous coordinates. This is just a linear transformation that guarantees that the set value doesn't change. It's, of course, not a coincidence that it looks very much the same as the homogeneous coordinates, because we introduced them in the matrix multiplication to say we need this additional line to carry along these factors that we have here, but this line should not influence the other calculation. And that's, of course, why we have chosen a line that doesn't influence the calculation. So if we want here also a line that only keeps the set value but doesn't influence the calculation, we get, of course, the very same, a line that looks the very same. But of course, be careful, we are in 3D now, so these are the homogeneous coordinates are then in 4D. So that means these are the homogeneous coordinates, and these are just the values that keep the set at the same level. Good. Now, of course, we want to do a rotation now in 3D, not just around one of the axes, but around a random axis. And of course, I've introduced this simpler case now because of this approach that we also had before in 2D when we said we have a more complex transformation. One way to do this is to just break it down in simpler transformations and then combine them with matrix multiplication to get the more complex transformation. And what we could here, if we know how to rotate around the set axis, then we could say, well, let's just take this vector here, rotate it to this axis, and that's also why it's called rotation around a directed line, because we have a direction vector here that we rotate, we map it to the z-axis, and then we rotate around the z-axis, and then we just do the reverse operation. The only problem that we have here is, of course, this is not unique. We don't know, like in a 2D case, when we're rotating around a point, we know, of course, if we shift that here, we have to shift that in the same way with the same vector to get the image here that we need to rotate around here. But here with the 3D case, this situation is not unique. We can move that in a way that this vector maps here, but still it's not, the relation to this vector is not uniquely defined with respect to this coordinate system. We could shift it in a way that this cube ends up here, or this cube ends up here. It is always, as long as this distance here with relation to this vector is always the same, these are all possible rotations that we can do if we just map this vector to here. So that doesn't work, but what works is to make this unique, we need a coordinate system. So what we are going to do is we introduce a coordinate system by taking two vectors that are perpendicular to this one, and then we map this coordinate system, let's call it u and v and w then, of course, and map that to this coordinate system. And then we have this position here uniquely defined. And then we can do the rotation around the z-axis, and then we can rotate it back. So wait, let's make sure that I use the correct rotation notation here. If we call this R or rot for rotation matrix, then this is the reversed rotation matrix, and this is then the, let's call it R set, because it's a rotation around the Z axis. So then we can do the transformation by this here. That's stupid notation, forget about it. Alright, that is our final transformation matrix. And of course we already know this R set here in the middle, because that's the easy case that we identified. Now all we need is these others here. In that case here, the reverse operation is actually very simple if you remember what these images are, what these column vectors are. The column vectors are the images of the base vectors after applying the linear transformation to it. And rotation is a linear transformation. So if we take these base vectors here and then apply this matrix to it, of course we end up with this very same coordinate system vectors that we introduced in the first place. So these vectors here are just the column vectors. The column vectors here are just the original vectors from this original coordinate system that we had. So we just have to write them down. Nothing to calculate here. And then, of course, we can make the inverse here. And then we get also the original transformation matrix, rotation matrix. If we choose them nicely in a way that we take unit vectors, then we don't even need to calculate it, because we can prove, or someone else has proven, and we can take advantage of that, that the inverse of an orthogonal matrix, that is a matrix where all the vectors are the column vectors are unit vectors and are orthogonal to each other, which is the case because they are just the coordinate system. If we choose them at the length of 1, then it's just the transpose of it. So we just have the vector u here as row vector, or as rows in our matrix, here the vector v and here the vector w. So we see we don't have to even calculate anything, we just have to write it down. The only thing, of course, that's missing now is this coordinate system, because I said we are defining it, but how do we get such a coordinate system that has also this unique characteristic that the vectors are orthogonal to each other and have the length of 1? And of course, I hope you remember, if we have 2 vectors, then creating such a coordinate system is very simple. We just use the cross product to calculate the third vector, which is then orthogonal to the original 2. But here we just have 1. And the solution is just use a simple trick. Just take a dummy vector t that is not linear dependent to this vector here, so it's not parallel. And you can do that, for example, if you have the simplest way to do it is if you have the vector w, just take one of the coordinates that is not 0 and set that to 0, because then you will never be able to make it a scalar multiple of the other, because you will always have 0 times 0 equals lambda times something unequal to 0, and that is for all lambda unequal 0 never fulfilled, and that means they are never parallel. So that is the easiest way to create such a dummy vector. And then that has a random angle phi, alpha, so we cannot use that, but we can use these two with the cross product here to create a vector u that is perpendicular to both, including, of course, the vector w. And then we have 2 perpendicular vectors. We can use that again with the cross product, to create another vector which is perpendicular to both of them, which is the vector v. And then we have our coordinate system. Now to do this here, of course, we also need to make sure that they have the length of 1, but it's also something that you should know how to do by just normalizing the 3 vectors. Good. One thing, of course, you have to notice is that this rotation, by defining this coordinate system, because we have chosen a random dummy vector here, this rotation is, of course, not unique, because we have by choosing a different, I call it dummy vector, of course, we end up having a different coordinate system. But the important thing is it doesn't have to be unique as long as we do always the same, as long as we apply always the correct inverse rotation matrix. So think about it. If you take that cube, for example, and you rotate it with the rotation matrix R1 to this position here, or if you choose a different coordinate system here, so we just have this one vector, and now we're creating a coordinate system. And depending on how we create that coordinate system, we might also end up here. And now we are applying this rotation around Z. And of course, we end up in a different position. But when we apply the inverse transformation here, R2 inverse, or R1 inverse, of course, we end up here at the correct position, which is the rotation here. Because of the way we again match it to exactly this coordinate system here. And in fact, we already had this situation in a 2D case. I just didn't tell it there because I didn't want to confuse you. Of course, the people who realized it might have been confused, so I'm solving this now. When I said for the 2D case, we're shifting the line and everything else with it down, I just used this vector 0, minus 5 to it. But I could have also said, well, this is our scene. We could have used that vector here. And then, of course, apply it to all other points, to the whole line, and all points here as well. But then we end up in the very same, we end up with this object, of course, in a different position. But when we shift them back with the very same, with the opposite of it, of course, we end up in the correct object here. So we have a different image of it than when we shift it, when we use a different translation vector. But if we use the exactly reverse of that translation vector, of course, we can do the linear operation here and end up in the very same result, because the linear operation is only with respect to the origin, and the reflection with respect to the origin is, of course, a different location if we start from a different location. But if we move it back, then we will end up in the very same location here for both cases. So you see here, this is not unique, but it doesn't have to be unique as long as the matrices that we use are matching. Good. So you see here rotations in 3D are relatively simple, but not really a directly generalization of 2D case, because we, but not because the mathematics behind it or the actual transformation is different, but because we have different options to rotate in 3D. And the same is, of course, true for reflection. In 2D, we reflect usually with respect to a line. Of course, we can also do point reflection, but usually we reflect with respect to a line. And in 3D, again, we can also do reflection with respect to a line, and it's actually a good exercise to try that, or reflection with respect to a point. But very often we reflect with respect to a plane. And again, let's look at the simple case here. This is actually an example. I don't want to go into details. You have a 2D case you will have in a new tutorial, and I'm not sure if a 3D case is also in the tutorials, or if it's just a hint that if you want to do more, then or we recommend to do more, and then this is an example that you could do, which is why I'm also not doing it here in detail, because if you listen to everything very carefully and understood it, then you should also be able to do it, to do this here. So, which is why we'll just illustrate the idea of it. Where we want to do a reflection with respect to planes. So let's again look at a very simple case first, which is the reflection in the xy plane. So for the 1D case, we said we reflection with respect to a line, and then we said, okay, if this line is y equals x, so this is the 2D case, then we said, okay, we realized it's just swapping the x and the y coordinates. So let's look at the 3D case. So these two cases are not related to each other. This is just as to refresh your memory how we we calculated this, we approached this problem. And in the 3D case, of course, we see if we reflect it with respect to the x and y coordinate, we see that the x and y values actually stay the same. The only thing that changes is the z value, and that just changes its sign. Actually, I should have drawn it differently, plus and minus here. That makes more sense, although it's technically not wrong. But yeah, usually we have plus at the top and minus at the bottom. So if this is z and then we reflect it at this plane, of course we get minus z. So that should be a plane that we get I have it written down. That's a plane that we get very easily. And then, of course, the interesting question is, how do we do reflections on random planes? First of all, random planes that go through the origin. And then the second question is random planes that go everywhere in our space, but not necessarily through the origin. For the origin, of course, we can also look, like in the 2D case, at the images of the base vectors. Well, we have the three approaches again. We can make educated guesses, which I think in that case is very difficult. So probably, I'm sure a lot of you will not be able to come up by just making a good estimate of it. We could look at the images of the base vectors. And since I don't have translation here, we don't need to look into the translation. So we just need to look into images of the base vectors, which we could construct, but it's also not really that easy. Or we could apply other transformation matrices to it that we already know. So for example, we already know rotation. So let me just illustrate the 2D case. That's also the one that you have in the tutorials. If we have a line here and we have that is supposed to go to the origin, we have an angle phi here, then of course we can rotate the line here with the rotation matrix. And of course, if we have an object here, we rotate also the object with the same rotation matrix. Then we can do a reflection here with a reflection matrix, and then we rotate everything back with the inverse matrix. And then we have reflected the object on this line here by applying these simpler transformation matrices that we already know. Now for the 3D case, we know reflection on the xy plane. So what we can do is pretty much the same. It's just a little more complicated because we have three orientations now. So let me draw this in a way that here we have B1, here we have B2, and here we have, pointing outside of the image, we have B3. So this is a notation, I don't know if I introduced this already, that if you draw it in 2D, 3D in 2D, that one plane is in line with your paper, then the notation for the third dimension is usually this here is pointing out of the screen or out of the paper, and this here is pointing into the paper. And the idea is of this, if you look at an arrow, then this is of course the look from the back, and this is the look from the front. Yeah, so this is, if we imagine it like this, then we have our plane somewhere here. And then what we can do is we can do, no, sorry, the plane goes still through the origin, so the plane is somewhere here. So we can then rotate this so it maps the line B1, but then it's still not in line with the x and y plane, so we have to rotate it also that it then maps to the to B. So it was B3, that is B2, to B2. Then we can do our reflection. Then we have to rotate it back and back in this direction, and then we're done. Is this correct? Let me check. Yes. And of course, if we have a translation, then we can do the very same thing. We just have to extend it by first saying we move it to the origin, then do the whole stuff here, and then move it back. So if this is, let's call this our rotation matrix R, I don't know, R star. Then here we apply the translation, which is this one. Then we apply R star, the reflection. and then the inverse operation. I'm almost done. Just give me one more minute. Good. So you see, this is a very complex thing, but you also see, hopefully now, why it is so convenient also to have this translation as a matrix multiplication, because that way we can really smoothly integrate it. Of course, creating this matrix is a little complicated, but once we have created it, and by splitting it in simple sub-operations that are easy to handle, we can easily create it. Then we have one single matrix that we can use for doing this very complex transformation with one operation, which is the matrix multiplication, and we don't have to do, for example, vector addition and matrix multiplication to achieve that. Good. Yeah, and you will have, like I said in a tutorial, a couple of exercises to practice that. Good. So, are there any questions? If not, then let me remind you that today there is a second version of the talk that we had also last Tuesday for the people who couldn't make it or were in the tutorials. And for all the others, there are tutorials. There are also practical sessions. And the practical sessions for the people who attend the talk, they will also be extended by 2 hours today. Of course, if you don't go to the talk, you are very welcome also to go to the practical session. Just be careful, the practical session then go from 1 to 3, but if no one's there at 2 o'clock, the TAs might then also leave, so be careful that you come in time. Good, then see you again on Thursday.